Okay, so take number 20. I'm going to be walking you through my Java code for A-star, the A-star algorithm, the A-star pathfinding algorithm. I'd go check out my video on basically explaining the A-star algorithm and its uses and applications, not code wise, but like logic wise and like how it executes. Yeah, so I'll go through my code here, and then in the other video I'll go over my my presentation. So A-star uses nodes. Each node is pretty much the same. So I made a nice little class for it. It has all its variables: heuristic, g, cost. The boolean is passable. A location, a point. This is over here. It's another class. A point, a location, like a coordinate, where it's located, and then a parent node. A simple constructor does all the setting, getters, setters. The f value, you might notice there's no f value up here. That's because f value is just g plus h. So I just made a little method, get f, takes the current g and h and adds them and returns that value. Yeah, it just makes a lot more sense to do it this way. In this class here, we have a point. It's very, very straightforward. There's two variables, an x and y. Get x, or it just has this little constructor, x, y, get x, get y, set x, set y. It's really just to visualize a coordinate, and then the node uses that just to get a location. Yeah. So besides that, you also see that there's another little method here. This method is used to compare nodes, and compare nodes f value and return the smallest one. This is used to sort an array list, which I'll show you in the A-star runner. Here, this is another one. This is the A-star runner here. And it's used to just sort f values from smallest to largest. And there wasn't really a sort method for nodes because it's a custom class, so I had to make my own little tiny method. And you'll see it implements comparable. So yeah, it sorts it from smallest to largest, and that's a crucial part of the algorithm, getting the smallest f values. So that's what I did here. As far as the A-star runner goes, it's structured pretty simply, but the logic behind it's a little complicated, so I'll go into that. It has a point start, a point end. This is just to get some data so that when the person or whoever's running it ends up using it, they can put in a bunch of different values for the program. For example, the dimensions of the map, the grid, whatever you want to call it, the x coordinate for the starting node, the y coordinate for the starting node. That should say y. The y coordinate for the starting node. The x coordinate for the target node, and the y coordinate for the target node. And those are just set here. And then we throw all that data into the 4 parameters for my A-star algorithm. And then it runs and it spits out, or does it? I don't think it does, or maybe it does. I don't know. I'll take a look through it. What I think it does is it sets up an array. It puts an array. It returns an array list of nodes, and then I have a nice little print method that can be used to print out everything in a nice fashionly manner. Before we go into that, we'll just look at some of the methods that this method uses. So this method calculates the G cost relative to a node, relative to this node specifically, and or to this node relative to point start. Just because that's where the G cost is calculated from. So you throw in the start point, and then you throw in the node that you're looking at, and then it basically just takes a total. I'll walk you through this. Total takes a variable of total G, and this will just keep adding itself. I keep adding 14 or 10 depending on different circumstances. Yeah, so here I have the loop here. Basically, grabs the parent's node. The parent, this is always hard to explain. It grabs the node that you're looking at, its parent, and then it checks if that node's parent node has a parent. I know it's hard to follow. If that node's parent node has a parent node, then it sees if that parent node, the node's parent node, is positioned diagonally or horizontally or vertically relative to the node that we're talking about. Yeah, I know it's hard to follow. It's a lot. It's way easier to see in the PowerPoint. It uses this little math. It's just a bit of math. It's not really anything that complicated. It just finds it's just like rise over run, to be completely honest. Just some basic calculus. This diagonal adds 14. If it's horizontal or vertical, it adds 10. And then if that is false, then the only reason that it'd be false is that the point that we're looking at, that we called, if the parent node's parent node is start. So we just use those values because start doesn't have a parent, and that'll give a null pointer exception, and that is not good. We do not want that. And then it stops when it reaches the start node. Basically, when the parent dot get parent is equal to null, and it just returns the total G cost. This method currently doesn't work. There's a null pointer exception. And that's something that really challenged me in doing this, and I don't know. It's all part of the learning experience. I try my best to figure it out. I'm quite proud of the logic, though. The logic makes sense. Just the code is a little bit buggy. So maybe that's something I'll return to in like maybe later, but we'll see. This method here just takes an array list and looks through it, and if this node here, the one that I'm highlighting, if this node here is in this array list, then it returns true. If it's not, then it returns false. So it's really just that. It compares it by location, because the only thing, the most unique thing about this is the location. So, yeah. Print path right here. This just prints the path. I mean, it just takes an array of nodes and it just prints them out by location. So there's a couple of brackets and a comma. So comma, or open bracket, X, comma, Y, close bracket. It does that for everything. And then here we go, the main event, the thing you've all been waiting for, the A-star algorithm. Takes the opened list and the closed list, and generates a grid with the dimensions that we declared up here, and the start points that we also declared up there. And basically we go through every single node in here and set their heuristic values relative to this coordinate. And yeah, because they're static. They're not going to move anywhere. They're not going to change, so you might as well just keep going through. It also, oh wait, no. That's all it does. Then we made a variable here for a node that will just keep getting stored. This is really just so that we have a place to store the information for a node without losing it. And then we start our loop. We have a Boolean here that will stop the loop when the target node is found, or it's basically within one, has a heuristic value of 1 relative to the end node. And yeah, we grab the surrounding 8. That's all this does. And if, alright, this is important, if it's passable, it isn't on the open list or the closed list, then we check if it's we check if it's the target node, and if it is, then we break out of the loop and we set the parent. We set the parent of the. Oh, what happened? We set the parent of the target node to the node that we're talking about, like current here, to current. And if it's not, then we just add it to the open list, and we do that for all the surrounding 8. Then, there's a little problem with this. We add the surrounding 8. This will generate an out of bounds error if it checks a node on the edge, because there's no. If we're talking about the corner, there's only 3 nodes there. We're missing 5, so I wasn't really sure how to fix that without hard coding it. And hard coding is very inefficient and takes a very, very, very long time. So I just gave up on that. Well, gave up's a depressing word. I just didn't do that because I just didn't. Not that I didn't have the time. I just found it very inefficient, and I can always come back to this and fix it. So once it grabs all the 8 and puts them on the open list, it basically calculates all the G values for each of the nodes on the open list, and then sorts the array list. So it sorts the open list by G cost, and then basically it just switches the current one that we're looking at, and the current one will become the one with the lowest F value. So we get the first, the lowest one, we set to current. We remove it from the open list and put it on the closed list, and then we start it over again. We keep doing that until we find it, and then it pops down here. It makes is where the path is generated, the node path. We grab the we make the start node equal. We make the start node's parent equal to nothing, and then we just keep cycling through until we find the start node, and then we keep adding it to the array list path, and then we just return path, and then that's it. Yeah, and that pretty much explains all my code. So yeah.